Connectivity sign-off, 5 ways to prevent costly errors. On overview, connectivity static sign-off is part of design sign-off. Connectivity static sign-off is become a critical aspect of design sign-off. This article covers 5 connectivity verification and sign-off requirements needed to stop connectivity error escapes while minimizing engineering time, especially as the connectivity requirements can vary between designs. What is connectivity sign-off? Connectivity sign-off is an exhaustive verification process which ensures that the path between the specified sources and destinations are properly connected and do not go through the disallowed logic or connect unspecified sources or destination. Connectivity sign-off is the 5 ways to prevent costly connectivity errors. Use comprehensive design-specific tiered checking. Connectivity sign-off applies connectivity rules during a progressive design stage to meet the functional specification for each design. Connectivity rules could be as simple as a signal driving a set of flops or more complex checks at the architectural level. Need to usually define a comprehensive rule set. To achieve sign-off, it's crucial to have a comprehensive set of rules. For example, on industry standard bus with multiple drivers or servers may need to have different connectivity depending on the design mode. Additionally, connectivity checks might be that all sources are connected to all destinations, only one source is connected to a specified set of destination, and etc. Example 1. Check the connectivity between the two flip-flops exist or do not does not exist. So the connectivity should exist between the FF source and an FF desti. And connectivity should not exist between the FFR source and FFR dest. So the example 2. Check that source 0 to 3 is connected to destination bus 0 to 3 without any bit swapping. Expected connectivity with visual errors. Example 3. Check for the mutually exclusive driver and receiver connections. If the design has a connection from A to C and the connected connection from B to C is allowed, the engineer should check both connections, one existing and the other not existing. Mutually exclusive driver connection. 1b. Create groups. Define clear rules and granular subchecks. The most efficient way to build a connectivity checking rule set is to first create groups on aggregate object for checking based on sources and destinations and a path of trading control. For example, to ensure UPF power schemes are implemented correctly, group all isolation cells and check the connectivity during the group. Another way is to use connectivity command to automatically create custom groups. For this, define and apply clear connectivity rules with granular subchecks in the tiers manner. Start by creating a sources S1 and destination 1 D1 groups. Then apply connectivity checks by step as shown in this example. This check connection. Step 1. Check connectivity. For example, 4 out of 9 instances are connected. Filter the 4 connected signal instances into a new custom group. Check connection. Step 2. Run another connectivity check using the custom group. The prior destination included in the group are now sources for further checks. 1c. Define rules to avoid redundancy. Connectivity rules should be defined such that there is no redundancy in the checking the same sources and a destination for different violation types. Paths from the source and destination can be checked for having not having combo logic in one rule that is checked for extra fanouts in another rule, precisely combining this functionality in one rule avoids redundancy to improve analysis and user review efficiency. 2. Perform early connectivity sign-off to eliminate critical verification holes at later design stages. It's important to begin connectivity static sign-off early before simulation or synthesis, then continue during the key stages of the AIP and SoC design process. RTL design stage. Validate connectivity for memory, power, and debug logic, and avoid glitches. Identify and remedy improper connections that could create complications when blocks are placed side by side in physical design. Post-synthesis stage. Rerun connectivity checks on the synthesized netlist to uncover new issues introduced, especially around power rail crossings. DFT and debug logic could affect implementation or test. Abutment connectivity checking. An example of a high significant benefit can be achieved with early verification is abutment connectivity checking. Some blocks are abutted in the physical layout and need to follow strict rules to avoid design failures, ensuring the compliance of the expected connectivity at LRTL can proactively avoid finding issues later. For the blocks of the abutted, various checks, for example open, tie, split, combo, loopback, and extra connection, should be performed. As shown here, the allowed arcs show top-level instances that are being checked for abutment compliance. Allowed arcs. So, 3. Understand connectivity static sign-offs, critical differences from former simulation and TICL scripting. Below a comparison of connectivity static sign-off with former simulation, with former simulation and TICL scripting approaches. 3A. Formal verification and static sign-off. Exhaustive verification. Both connectivity static sign-off and formal methods perform exhaustive verification, but the combination of a static sign-off, speed, and capacity enables it to fully analyze both short and simple paths and complex paths with multiple sources and destinations. Performance. Static sign-off has analyzed tens of millions of gates in about 3 minutes, including reading and design to create a database with only a few minutes of analysis time. This is order of magnitude faster than a formal verification, which can take hours. The static sign-off also performs well on single CPU, while formal requires multiple cores. Memory usage of static sign-off is estimated to be less than 1 GB per million gates. Capacity. Static sign-off can analyze billions of gates in a few hours without requiring black boxing. This can include checking billions of paths from the multiple sources or destination very efficiently. Formal verification, however, typically supports only a few billion gates, even after using multiple processing cores for analysis. Connectivity static sign-off's performance is orders of magnitude faster than a formal method. 3B. Simulation and static sign-off. Coverage. With the simulation, coverage depends on test vectors, test benches, and VIP availability. The checks only cover conditions explicitly specified in test vectors, so designers cannot guarantee all conditions are covered. Additionally, to try to glitch checking during simulation, an engineer would write assertions to do limited glitch checking for specific points. Static sign-off are user-defined rules automatically cover all conditions. If the engineer specifies a source destination pattern, it will cover all destinations. Similar to simulation, connective static sign-off checks whether the destination has the expected value for a specified source or constraint values providing the basic expected checks. Checking expected value at a destination. Feasibility. Certain checks are only feasible in static sign-off and not simulation. Some examples are 1. Conforming bits aren't swapped. C1A for example 2. 2. Verify only one source drives multiple destination. C1A example 3. 3. Checking physical connectivity only by verifying the proper abandonment. C1B. 4. Confirming the connection does not exist. Static sign-off will flag that the specified connection does not exist in any situation. Simulation will not flag the connection does not exist if other signals drive destination to the expected value. So, does connection from A to B exist? Confirm there is no extra fan-out. Static sign-off will check whether A is connected to B and check for an extra fan-out. Simulation will only check that A is connected to B. It cannot connect for an extra fan-out. Further, because static sign-off rule creation is dependent on test vector or test bench availability, the sign-off step can start very early in RTL design. 3C. Ticker scripting versus static sign-off. Rule creation. Ticker scripts require complex coding and ongoing maintenance for connectivity checking. In contrast, static sign-off uses efficient, flexible commands with minimal rule specification or maintenance effort. Performance. Ticker scripts take hours to run just one block, which static sign-off can complete in minutes. Only versus less sign-off, ticker scripts run only on that list, so checks do not occur until after synthesis. Static sign-off can be run during RTL, enable early detection of connectivity error and reduce unnecessary iterations. 3D. RTL linting versus static sign-off. RTL linting sign-off is focused on ensuring RTL quality for the selected rules. Connective static sign-off goes further, understanding more of the design functionality, including power, and performing more explicitly checks across the entire design. It also supports constraint-based connectivity and glitch checking. 4. Tool usability can make or break the sign-off methodology. For connectivity verification, a sign-off tool to be widely adopted in the design methodology, essential that tool be easier incorporated and minimize design effort. Below are 6 key factors to consider when evaluating connectivity verification sign-off tool. When a tool can analyze 100 billion gates in only minutes, it becomes feasible for engineers to connectivity sign-off as part of the design process. Connectivity error-free design becoming feasible if tool has capacity to sign off multiple billion gates SOCs. Low noise reporting. Low noise reporting reduces reviews and debug time. This can be achieved after irrelevant issues can be filtered out by specified conditions or constrained on structural check. Automatic verification violation classification into sub-check categories, such as in miss-orbit breach, give designers precise control over which rules subchecks are analyzed and reported. User-defined flexible rules. The connectivity checks needed depend on the design requirement. Thus, the engineers must be able to quickly define compact rules for various sources, destination, and combinations, connection types, and glitch checks. The tool should allow the flexible rule definitions, both broad and specific, for example, capturing all flip-flops, or limiting the particular models, and support to place in rules, route and rules such as abandonment checking. Efficient rule creation. Efficient rules creation and safe weeks avoid manual errors and improve coverage. For example, the tool should require only a few commands to define a block level or SS level check to verify the validity of connection. Automated object aggregation. A connectivity checking tool should automatically aggregate key objects for the checks, such as power, control objects like isolation cells, which are spread across the chip. Manually collecting them is impractical, so the tool should allow designers to automatically create groups of objects either chip-wide or within a specific hierarchy. Negative test mutually exclusive as custom groups. The tool should check for both connectivity and non-connectivity and allows engineers to automatically create custom object groups, for example, for signal or instances. One command should generate the desired object dynamically, while another can utilize those groups. Additionally, should report to mutually exclusive connections, such as violation like if A to B and C to B is not allowed, or if X to Y and then Z to G is not, X to G is not allowed, and automatically identify the flag these connection violation. 5. Glitch checking is needed to ensure connection integrity. Connectivity checking should include glitch checking to be complete. A glitch is a signal transition with a duration shorter than a system clock period. Glitches can lead to functional failures, especially when they occur on on-time paths. A transition to selected line of a multiplexer can induce a glitch at the MUX due to the unequal combination delays along with the data input paths. This glitch can propagate through downstream combination logic and arrive at the input of receiving flip-flops. If the transition occurs near the clock edge and may violate timing constraint or place the flip-flop in an indeterminate state, potentially resulting in functional errors on on-time type paths. A glitch can cause unexpected system behavior leading to functional failures. 3. Conclusion. Maximizing connectivity sign-off efficiency. The role of the static sign-off continues to expand, with the connectivity static sign-off offering design teams user-defined rules and fast performance, low noise, and broadest coverage, eliminating the limiting restriction associated with the formal verification, simulation, and ticker scripting. About the real intent safe connection. Real intent safe connectivity, glitch, and glitch sign-off tools beats all the key connectivity verification metrics discussed above, eliminating missed errors while minimizing designer effort. 1. Analyzes tens of millions of gates in only minutes. 2. Create low noise violation reports with filtering and control over checks and subchecks. 3. Support user-defined rules. 4. Offers efficient rule set creation, saving weeks. 5. Allows negative testing, mutually exclusive rules, and automatic custom object groups. 6. Performs glitch checking to ensure the physical connectivity integrity. Okay, today I read this article, Connectivity Sign-Off, 5 ways to prevent costly errors. Thank you for your time. See you next time.